Alrighty, so we're recording. So we are going to be looking at merge sort and one other sort this week, which is called quick sort. They're both recursive. So one of the things we want to do is strengthen our ability to visualize recursive pattern and start to think a little bit mathematically about that, because some of our analysis depends on our ability to sort of visualize it, but we're not going to torture you too much with that. But it is a good skill to start developing, because if you take a higher level algorithms class, which some of you might, you're going to be expected to do some more rigorous mathematical evaluations of some of the costs of these things. So we'll try to introduce you to some of the ways to think about that. And we might circle back and pick up some of the math on that a little bit once we get comfortable with a lot of this stuff. So today is all about merge sort and some fundamental kind of visualization techniques that we'll, exercise using simpler algorithms before we kind of tackle the merge sort one. But of course, we have our homework due tonight, quiz one and quiz one as well. Don't forget that quiz one. Thanks everybody who got your homework in. It'll take me a little while to grind through all the data so far. All of the Google spreadsheets, except for one or two, have been accessible. So I appreciate you guys sharing that stuff and checking it. Our lab today is pretty straightforward. It's just another divide and conquer, kind of guess my number thing again, but this time it's going to be recursive. So give you the prototype function for that, and you can just kind of grind away at that pretty quickly. And then we'll do something for lab 6, which is a problem that I've made up. It doesn't make a lot of sense maybe mathematically, but it forces us to do something very similar to what the merge sort is going to do today, which is do something from the bottom up. So we'll talk about what it means to have sort of a bottom up recursive process. It's subtle, but really, really tricky to kind of realize, and it might teach you something about recursion that maybe you hadn't really noticed before. So both the merge sort and lab 6 should demonstrate that capability. So we'll kind of pick that up. And we'll also introduce our homework too. It's one of my bizarre creations called The Lost Amulet of King Obfuscate. And if you know what obfuscate is, I'm trying to make a joke there. But it'll be a divide and conquer in two-dimensional space problem. So we're going to be dividing and conquering for merge sort in a one-dimensional space, namely an array. But homework 2 is about searching for something in a two-dimensional space using divide and conquer. So hopefully you find that entertaining. We'll cover that here before we get things wrapped up today. And then, of course, our quiz 2 is out there in front of us. So all those links should be on Canvas. Hopefully I didn't break anything. I've been trying to get Program IZ Pro versions of everything up there so people can download from that if they like to. Remember, for our homework policy, especially if you haven't had my class before. So, and this is really tradition for all CS courses that you might encounter in four-year institutions or elsewhere. Unlike maybe some other classes you might have here where it's perfectly fine, mostly in CS, you're pretty strictly forbidden from like looking at each other's code, talking about your code, talking about if it's a puzzle class like this one, what your solution was. Sounds kind of Machiavellian, but I'm just trying to get you guys used to what is expected out there in the world to my best assessment. If I look at Berkeley's, computer science department, there's a lot of thou shalt nots and some pretty scary language about, what'll happen if you do these things. I'm a little bit more reasonable, but I try to adhere to those kinds of policies because it's just kind of how we all sort of should be thinking anyway. So, and of course, asking AI to write your code. It's just kind of a short path to not learning anything. So if you get stuck or you're feeling the pressure, let me know. We'll have a tutor here to help us. Jake, some of you may have met Jake, will be joining us once he gets clear of a few other things he's got to do. But hopefully we can help you get through the parts that are stuck. Okay, so if you have any questions about that, let me know. Now with labs, feel free to collaborate. That's more of a formative kind of thing. The homeworks are more summative, which means we're trying to assess your individual ability to solve these problems. So hopefully that's not too much of a bummer. I don't, if it's not in the Canvas directly, then it would be in one of the README files associated with that. So let me just pull that up real quick.
Where can you find it?
So there is not one. There's not one. Thank you for pointing that out. So that one, unless bear with me here 1 second. Let me just pull up the Pro and see if there's a README there. Some of these things, as I've been transferring them over, the rubrics have gotten lost. No, there's not one on that. So it is 100-point problem, and that's on me. That's just one of the few that probably don't have a clear and solid rubric on there. I thought I did, but let me get back to you guys on that one and get something posted for you. But all of our homework assignments will be normalized to 100%. And usually I'm looking for, adherence to the prototypes that have been provided, if that is the case, and just basically following the instructions that are laid out there. But almost always I'll have that stuff broken down. So that's one that looks like it got past me. Thank you for raising that. Again, just a reminder, if you're still grinding through your data, you can always look at a CSV plot. It's pretty, once you download the file, depending on where you're getting it from, which platform you're coding in, just load that into CSV plot and it should be ready to go. And in general, remember that if you want to ever add a comment to your submission, you can do that. You can add an extra link as a submission comment, and I can find that no problem. So don't worry if you've already submitted one thing, but I'm asking you to submit two. You can just sort of add that as a comment. If you bury your link somewhere in your code, just let me know. Sometimes I go looking for it and I can't find the link to your Google spreadsheet because it's a comment in your code. Just give me a little hint and I'll try to dig it up. So the only thing I'm going to start to probably not like very much is pasting of direct code into the comment section in Canvas because all of the indentations goes away. I don't think anybody's doing that. You're welcome to upload a file. You're welcome to use Program.is or some other cloud hosted link based solution, but the pasting stuff will be problematic. Okay. So I think everybody so far is in pretty good shape. And of course, again, just stick with Canvas. Again, I think everybody's doing a great job on that. So I really appreciate you guys sticking with the program. Most of you have kind of been around the block already and kind of know how I kind of run these things. So thanks for that. Late policy reminder, if you somehow at any point in the semester get into a crunch and you can't get it done on Tuesday, or let's say you want to take your best shot on Tuesday, not knowing what you're going to get, and then you wake up Wednesday morning and you think, I totally know what I did wrong. Submit it again, you might be able to improve your grade. Okay, so I'll take whatever your most recent submission is. If I can peek at your stuff early, I will. But generally I won't get to it until Saturday or Sunday because I just got like 70 students this semester. But you can submit as many times as you want, and you can max out at 90, 80, 70, 60, depending on, how late your code is. So it's not like you can do worse than your initial submission. You can generally only do better by trying a second time. Okay. So hopefully that clarifies things a little bit. So today, divide and conquer. We'll do a little brief look at homework 1, lab 3 stuff, and then dive deep into recursion, and then introduce our homework 2. So this is my own personal little joke. Tennis has been taken over by pickleball, for those of you who don't know the sport, which I predict will soon be taken over by table tennis, which will soon be taken over by something else, which is a little recursive joke, of course. So let's flash through about 3 slides here. Remember that the shell sort, as obscure as it is, kind of will let you know you're dealing with shell sort when you are dealing with this concept of gaps, which is really just using an insertion sort on these sort of interleaved sections. The blue section, slide over the same insertion sort on the orange, etc. Then change the gap. 5 gap, 3 gap, 1 gap. When we get down to 1 gap, we're doing an insertion sort. And weirdly enough, this idea of gaps is kind of something that's going to come back to us in a sense throughout the semester when we do hashing, like finding a place to store something that, something's not already in, kind of musical chairs. Choosing prime numbers turns out to be a very useful thing in a lot of scenarios because we kind of don't end up revisiting the same chair all the time if this was a musical chair scenario. So these gaps that we chose for shell sort, kind of using a similar strategy. We sort on fives, then threes, then ones. That's going to converge more quickly to a fully sorted list. So really interesting idea that sort of transcends just the shell sort, but the idea of using prime numbers to avoid looping or repeating over the same space over and over again. It's kind of a cool trick in general, a good one to know about. Prime numbers are kind of right up there with modulo in terms of some of our best friends mathematically for doing cool stuff. Okay, so that was our shell sort from last time. Sorting algorithms, high level look again. Bubble sort, insertion sort. These are stable sorts because they don't necessarily, if implemented correctly, they don't swap things that are already equal in value. Selection sort is unstable. Shell sort is unstable. Of course, shuffle sort is unstable, but linear. And these are quadratic. So n times n, roughly. Shell sort is maybe a little better than that, but not much better. And also, it doesn't align very well with modern hardware. We talked about thrashing the cache, L1 and L2 caches on modern hardware, so that tends to be a problem. This week, we're looking at merge sort and quick sort, similar but different approaches to using recursion to solve this. Divide and conquer predominantly, but some of these can be implemented in for loops. And we'll look at that briefly today for the merge sort, just to show you that you can do it both ways. But still, fundamentally, it's going to divide the problem down, 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 and we get some theoretical benefit from doing that little division, okay? So new terminology for us today, and you'll see this on quiz 1, linearithmic. So if you have something that is essentially you're sorting n things and it takes n times the logarithm of n, which may seem like a weird equation, then that is what we call linearithmic. And today we will see more or less visually where that n times log of n roughly comes from. So, but the key word there is linearithmic, and both of these sorts are linearithmic, which if we look at the Desmos graph of all of our popular curves, we'll see that quadratic really hockey sticks up much faster than linearithmic, which is different than logarithmic, right? Linearithmic is between the log 2 of something, right? Log kind of does this. Boop. Linearithmic sort of looks kind of linear, but it's a slow climb, and then you got your quadratic doing that. Okay? So we'll slowly introduce, more and more algorithms that fit into these different slots. Okay. So that's our over logarithms. Now, here's a good trick you want to know about. Of course, you should know what logarithm means. I won't go over that again. But what's really nice is if you've got to do something in some weird base and you don't happen to have a function for that particular base, you can just do this trick. Whatever base you have, do this. Log of that of some random base of 16 divided by some log of a random base 2. And that's going to give you the same result. In other words, log 10 of 16 divided by log 10 of 2 gives you 1.2 or 4, etc., equals 4, okay? Which is the correct answer for this. So it's just a nice programming trick when you're trying to calculate a log, but you don't have the base around that you want. So again, log base 2 of 16, that's a 4 times 2. 2 to the 4th power gives me the 16. And so we can calculate that 2 different ways. Okay, just a little shortcut. Oops, little accidental extra animation there. Sorry about that. 4 of those guys. All right. Okay, lab 3, just a quick retrospective. So great work, everybody. So most of us got 3, compares average with the 1, swap. A couple folks found some little nips and tucks around the outside edges to get us to 2.5 with an average swap of 1. Well done there. Turns out there's a couple, there's probably no name for it, but if you tear it down, you're basically going to use either something like an insertion sort or maybe a bubble sort to achieve this. And there's a lot of little variations in between. And we can haggle around the outside edges about what's a copy versus a swap. But basically, that's about our threshold. We can't really do better than that, for a general case. Now, some of you were sharp enough to realize that, hey, you were really only testing 1, 2, 3, so I don't have to worry about 15, 16, 17, so I could use maybe a counting sort approach. And yes, that is better than you could do with all of our other algorithms, because these other algorithms are fundamentally quadratic. So you can do better than quadratic and approach essentially what is a linear type of cost for that. But, it's not general. It's just saying, oh, I know I'll only have a 1, a 2, and a 3, which is fair. It's a fair way to actually kind of size up the problem. So hopefully you had a little bit of fun with that. There were no real, wrong answers. Well, there were wrong answers, but there's no bad performance on that. Here's just one way to look at it. This was one of my implementations, which is really a bubble sort if you think about it. I compare 0 and 1 position, and if they're out of order, I'll swap. And then I'll compare the 1 and 2 position, and if they're out of order, I'll swap. But if I don't swap, I know I'm done, right? There's no point to continue. This was one of those optimizations we learned from the bubble sort. We don't really need to keep swapping or keep trying if we didn't. Otherwise, we just go back and our size got 1 less than it did last time, so we only have 1 more compare, and we can get out of there. Okay. So the insertion sort version of this with loops and everything was equally good and is essentially doing the same thing, just in a slightly different format. So both of these are just a little bit better maybe than some of the other stuff that folks might have done, or maybe there's an extra step somewhere where maybe you weren't kind of optimizing. But again, no points off. It's just interesting to see how you can get it down as minimal as you can. And there's probably ways we could use assembly code and make it even more fast than if doing it in C++, but we're not going to quite go there. Now, a reminder for tonight, again, for folks who are still kind of digging around in this, I apologize. This is kind of the last time we'll be doing this kind of thing, but notice that if we're doubling the size of n each time, and your swaps are sort of growing by a factor of 4, or just matching up with what the quadratic computation results in, either at n times n or at n times n minus 1. These are both quadratic, essentially, right? So if we plug and chug in, right? So if your numbers are paralleling those or off by some constant factor, then we would say, okay, I'm growing in a quadratic way, even if you may not match exactly. But sometimes the algorithms we write match exactly, because that's how they're actually structured. Now, timing is a little less clear. So one hallmark over there is just dividing, we said this time by this time. And if that is kind of settling in eventually around 4, you can see it kind of wobbles here, right? Slow, fast. That's probably network traffic there in our case, right? Because we're kind of using a cloud-based solution. You can kind of see as n gets bigger, it starts to stabilize in and around 4, right? And so essentially the trick is to realize you're growing by 4. And if you need to estimate and predict, you can just sort of like, do that empirical analysis. We're really just looking for an approximation, and then multiply the time 44 by 4 by 4 by 4 by 4. And of course, that should get you to your final estimate for your last question. Okay. That's if you're kind of essentially doing a quadratic algorithm. If you're doing it n log n or something else like that, you'll see something slightly different. But most of us will have tried to tackle a quadratic sort on this one. Okay, so that's just one insight. And we don't need to be experts at kind of seeing curves by looking at numbers, but we want to feel grounded when we talk about these terms: quadratic, n times n, and eventually logarithmic stuff as well. Okay. So hopefully that gets you to the finish line okay. Let's switch directions and talk about recursion again. So, of course, it's a technique. Most modern languages support it. There's some subtle things about it. Many of us might know, but I'm going to try to highlight those things today. You can do many things with for loops, but there's an elegance to writing it recursively. And sometimes there's just no other way to do it except with recursion. Later in the semester, we will be tracing our way through linked node structures, pointers, the dreaded pointer, and we will be doing it recursively. So it is really important for us to get our heads wrapped around this recursion thing in a controlled environment, which is, what arrays are, before we move off into crazy pointers going all over the place. So that's why we spend a little bit of time on this right now. Okay. So yes, many of the things we're going to talk about this week can be done with loops, but where we're going, not so much. Okay. So, and it's just a critical thing to really understand, and I'll try to help you much as I can. Let's take a look at the venerable factorial function. We all know that factorial 4 is 4 times the factorial of 3. Okay. Many of you saw this in my class before. So we can think of it as a recursive function. And if we know the factorial of 3, it's trivial. But if we don't, we just keep applying the same rule until we get down to our base case, which is factorial of 1 is always 1. Okay. So we can implement that in a recursive function, right? So here's just, a little more obvious than maybe you want to you want to deal with, but we're just basically saying, hey, I'm just going to call myself recursively to solve the remainder of the problem that I don't understand yet. So in the general case, that's n times factorial n minus 1, which could be an infinite loop unless we have a really good base case, which many of us know from doing some recursion already. Okay. But let's take a look at what is happening in memory. This is the important part. So let's just say that I wrote 3 functions, one called factorial 3, one called factorial of 2, and one called factorial of 1. And I try to calculate the factorial of 3. So many of you would probably know at this point in your coding that the factorial of 3 function waits around for the factorial of 2 function. Right? And the factorial of 2 function waits around for the factorial of 1 function. They stay in memory and they remember where they're going to return to when the function returns, right? So I'm going to get my value here and then incorporate it and then go back to wherever I came from. So this is a really important thing for understanding what's going on with recursion. Because just like this example, recursion with true recursive function calls is really going to do the same thing. Every recursive step waits around in memory for the next recursive step to finish. So if it's kind of a linear depth first thing like this, then it's kind of like going down an elevator and coming back up. And so the unwinding we'll see in recursion is this part, right? Coming back up from the base. We don't skip levels. We got to go all the way back up to the top. There is no skipping levels unless we have an error of some kind or what we call an exception. So many of you might remember the dig, 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 up, up, up lab we did in Comp 130. So that was really kind of a warm up for this, okay? Obviously, we don't want to write factorial this way. That would be a silly way to do it. So we put in a proper base case. If n equals 1, return 1. Otherwise, call yourself. But we're not going around in a circle here, okay? Don't make the mistake of thinking we are just calling a loop. We are not doing that. We are replicating the function in memory and giving it a different value every time and then waiting around for the return or the unwind. So here is the full proper factorial, right? So it's the same function, different copy in memory. We have an n equals 2 and n equals 3. This one is not going anywhere, and this one is not going anywhere until the unwind. So you might ask yourself, where does it return to? Well, this one is going to return to here, and we still got to do this, right? We're not done yet. This one's going to return to here, and we still have to do this. So we have to imagine whenever you have a recursive problem, imagine you're kind of, on an elevator going down underground halfway to the bottom. There are floors above you and there's floors below you, right? You don't know what floor you're on. All you know is what your job is, okay? That's what recursion is really like. And it's not always going to be linear, as we'll see here in just a minute. It can branch out and make trees. So we're going to explore that kind of pattern as well here in just a second. Okay. So there's our unwinding, which will be crucial for understanding really the merge sort today. Okay. Now, true thing, if I say factorial 100 with this kind of code, I'm going to have 100 copies of that function in memory. Not very efficient. So recursion isn't really free. It takes up memory. So if you have an algorithm that needs to go to 10,000 levels deep in recursion, let's say chess, right? You're going to solve chess with recursion, probably not going to happen, right? Or maybe solve a Rubik's Cube using recursion, probably not going to happen. Maybe it will, but those are really, really, really deep recursive solutions. And, we can't, in some cases, calculate all those possibilities, okay? Think about a chess game, the opening moves, it's like what? There's 19 ways to open, and then those 19 branch out, and those branch out. That's a big, 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 big tree, okay? So there are limits to what we can do with recursion, but if we're never going to really go too deep at any one time, we might be able to pull it off, okay? So here's a different way of doing the factorial code that you might find interesting. Here, we're saying we're going to do a portion of the factorial problem from start to end inclusive. So I'm saying, okay, factorial to 1 to 5 or factorial of 4 to 8. So we just get to pick the region. So why would I do this? Well, this allows me then to, well, first off, handle my base case. If these two things are the same, then just return either one of them because they're the same. That's the base case. Otherwise, let's break it in half, right? Or let's break it not in half, but let's just break off a piece and say, I'll go from start to n minus 1, and then just I'll multiply it times n. So it's kind of like the one we just saw. We just sort of changed this a little bit so we can do a partial. We can pick any subsection we want. And that's going to open up the next step, right? The next step is to say, oh, instead of just peeling off one, let's break it in half and go left and right with it, okay? But here we're just sort of saying, let's just kind of stay close to what we were doing last time, right? So we're just sort of saying, hey, factorial of 4 to 8 is 4 to 7 times 8, right? 4 to 7 is going to be 4 to 6 times 7. So all of these factorials are waiting around in memory, of course, for me to unwind and build up the answer, which eventually gets returned as a part of that function. Okay, so that's the first step. We're just sort of doing it by calculating this and multiplying it times the n. Okay, so we kind of have this long linear chain of calls to factorial. And we can kind of envision that as an elevator going down, 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 back up, 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 up. Okay. So that's not too hard to visualize. Okay? And just a precision notification, if you try to go above 10 or 11, you actually blow up the precision pretty quickly. So you're welcome to try this code here. And when you run it at 12 or 13, you're going to see you start getting negative numbers or a 0. That means you've gone beyond the 32-bit capability of the default integer value. If you switch that to a long in C++, now you get the full 64-bit precision in integer form, but you still have pretty limited upper ceiling on how far you can go if you're really going to try to do some really, really big numbers. So we'll see here in a minute that Python 3 actually has unlimited integer precision. It's pretty crazy. So it's a joy because if you've ever wanted to do like encryption with large numbers, and C++ has libraries that'll do it, but Python just does it. It just dynamically adds precision on the fly. Doesn't do it nearly as fast as C++ does, but it will actually do it and you'll get an accurate result for your integer math. But in C++, we have to take some extra steps if we want to go that big. but that's not really the focus of this class. But let's take a look at changing our tree from an elevator that goes down, down, down into a branching structure. So here we're going to calculate a midpoint and call left and right side. Now, this is a single threaded application, which means we can only go down one branch at a time. So if we go down the left side with that first recursive call, you can kind of imagine us coming back, but then we got to go down the left side again, and down the left side again, and down the left side, and again. So we're branching in the left direction as far as we can go until we reach our base case, okay? And then we get to unwind back to here, and then we got to go down the right branch, okay? Then we fully unwind, right? Go back to the previous level, and we probably have to go down and go left, left, right, up, right. So we're going to have this sort of traversal structure that's going to slowly fill out this tree where we're going up, down, right, left. And the dominant flow is going to be figure out everything to the left first, and then back up and explore the right, okay? So suddenly our simple elevator down, 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 up got very complicated. Okay? And so the challenge for us starting out is to try to imagine what the final shape of that tree is going to look like. It's going to be a, binary tree basically with left and right branches, but it's only going to explore one pathway at a time and then unwind. So it's going to clear out the memory after it reaches the bottom and go back up and then dig down a different way and then go back up and dig down a slightly different way. So just this little left-right split creates a fundamentally different recursive structure that we're going to end up following, okay? And at each step before we return, we put together what we learned from the deeper levels below us, left and right side, and return that not to main, but to the next level above us, okay? So it's an exception that we're going back to main. Only the very, very top level, of course, returns back to main. Typically, imagine there's at least a couple rooms above us. That's probably a better way to think about it, okay? So lots of ways to implement factorial. It's a great way to visualize recursion, but not probably the most optimal way to calculate a recursive or a factorial number. So we're just sort of taking advantage of it because it's easy to visualize. Left, right, right, split, and on we go. Okay. So wouldn't probably divide and conquer with factorial unless maybe we were on a multi-core computer and we could say, hey, you core, you go take the left side and you take the right side, right? And maybe there was some, parallel stuff that we could do with that. That's the kind of stuff we explore in advanced C++. So if you're interested in that, come back in the springtime and we'll kind of do that. So the other thing to keep in mind is the traversal path does not keep everything in memory. So here's us calculating factorial 1 to 8. So we say, oh, okay, break it in half, do the 1 to 4. Oh, 8 around, I got to go do the 1 to 2. Okay, now I know the base case for 1 to 1. Go back up, right? Finish the 2. Go back up, finish at the 1, 4. Okay, so when these things go away, it frees up memory. So we're not really ever holding the whole tree in memory, right? We're just exploring to the deepest level, backing up, going down again. So if my range was 1 to 8, the question is, what's the maximum depth we're ever going to hit when we're dividing in half every time? Okay, I'll let you think about that for a minute while we explore the rest of this, right? So we unwind, we unwind, we unwind, we explore down the right side, okay? So remember, we can't go up unless we've done the left and the right. So I do the left there, I go back up, I do the right, go back up, haven't done the right yet, so I got to do the right. Oops, got to go left first, then the right. Why is it left, right? Because that's the way we wrote the code. We could rewrite the code so it goes right, left if we wanted to, but we wrote it to do the left side first, okay? So this is what's really happening in terms of the functional kind of functions that are waiting around in memory for us. And eventually we get to the top with our mathematical answer. That's the beauty of recursion, is once we set up the pattern, we let, the programming environment do the replication and tracking of all the return of information. Okay. So if I was to say, how many functions are active at any one time, you'd say 4, which turns out to be, 2 times 2 is 4 times 2 is 8. It's kind of log base 2, depending on how you count. Do we count, this level here or not? But if we take log base 2 of 8 and add 1, we're right there where we want to be, right? We've got 4, a maximum depth of 4. And so very often when we talk about depth, we treat this as depth 0, 1, 2, and 3, okay? So, but as n gets bigger and bigger, you'll see that the log base 2 calculation dominates the correctness. It's not exactly right down to the very, very last node, but it basically gets you exceedingly close to the correct answer, right? You just need to know what n is and that you're dividing by 2. Log base 2 is going to put you right where, right near the final answer, right? But if I were to say, how many nodes did we visit the whole time? Then you would have to visualize the whole tree. So if I said, how many times did we call the function? Now you got a different question there, right? You got to figure out how many nodes or branches are there in the whole tree there to find out that answer, okay? So those are important questions when we think about performance, right? So there is our visualization of our full tree, but we never had all of those things going at any one time. But if we want to analyze the cost of this function, right, the way it's written, we want to imagine that tree and say, oh, well, I had to visit all those things, and maybe I did some work in every one of those boxes. So how would I calculate how many boxes are on the screen there, knowing that I started with an 8? Okay. So that is the doorway to really analyzing the performance of some of these divide and conquer problems. Okay. And divide and conquer by 2, right? But you could be divide and conquer by 3 if you wanted to try to do something like that. That's a log base 3 kind of situation. Okay. So keep that in mind for your homework. So when you're thinking about homework 2, you're not dividing a linear space, you're dividing a 2-dimensional space into quadrants. So we're going to have something a little bit different, but it's not that far away from what we're doing here with these numbers. Any questions on that so far? Okay. All right. So now multiplications, if we're multiplying these things together, right? So here we're just going to be adding up the number of times we multiply, right? So it turns out that it's linear. Okay. So we really, in doing the factorial this way, we didn't buy ourselves anything more than if we were doing it in a loop. So it's kind of maybe a little silly to use recursion to do it, but it demonstrates the pattern that, we're going to see over and over and over again. But it's a little bit of a trick question. If I said, hey, we're using divide and conquer, what's the performance of this? You might say, oh, it's going to be log base 2 or log of n. Not so much, right? If I say, what are the number of multiplications? Okay. You just have to think about where that's happening. It's happening here and here and here, right? Between these numbers. And then it has to happen here between these numbers, right? So you can kind of figure that out. But so that's the kind of game that we play. So that's our divide and conquer. Now, if we have unsorted data, so this is an example of your worst day ever, right? If someone said, hey, I need to find 35 and I want you to use divide and conquer, and oh, by the way, I didn't sort the data ahead of time, okay? So those red lines kind of represent the division each time we do a recursive step, okay? So with the traversal starting left first, we're going to come down here. We're going to look all over here, and you kind of see 35 is way over here. Okay. So it was an unlucky day for us. We wrote our code to traverse left first before right. And so it kind of put that 35, way out of touch. We might have gotten lucky if we traversed right first. We would have got it at the first maximum depth we reach, which would have been much, much faster. Okay. So we're always going to be thinking about worst case versus best case versus average case. Okay. But there's really nothing that we can do here to improve our worst case situation. It's always going to end up being at some point, I got to look at every single number before I can actually find the thing. So it's not that divide and conquer necessarily buys us some performance increase unless we have, maybe something ahead of time done, like we've already sorted this information, right? So let's take a look at that. So, well, first off, the cost of this in doing comparisons, right? So are you my number, right? Are you my number? Are you my number? I'm sort of, recursively getting all the way to the bottom to figure out whether that's my number or not, which is kind of a silly thing. So I have 16 comparisons at the very leaves of my tree, and I don't really do any comparisons until I get all the way to the bottom. So I get to the bottom and I know the 17's not it, then the 2's not it, etc. So that's where the work gets done, at the very depths of our recursive travels. And we do 16 checks, and that's no better than a linear search. Okay. So 16 compares, is just as good as just searching linearly through there. Now, if I sorted this, which, we're going to be kind of dealing with in our lab today, if I say, hey, is the number less than 11? And you say it's greater than, then I have divided everything in half. Now we're doing some good work, okay? Because we're never going to go visit that left half of the tree. And then you say, okay, it's less than 44. Okay, is it greater than 15? Is it greater than 21? Boom. Maximum depth, right? 0, 1, 2, 3, 4. Log base 2 of 16 things. Okay. And we got that benefit because it was pre-sorted. Okay. So when you have things pre-sorted, you can get a logarithmic or log base 2 performance out of it. But if you're doing the sorting for the first time, as we'll see here in a moment with merge sort, we still got a little more work to do. So once somebody is sorting something like a dictionary, we've all flipped open a dictionary and realized I got to go left or right, right? That's because someone sorted the dictionary ahead of time. When we have to do the sorting, it's going to be worse than log time. It's going to be something typically like n log n, which we said is linear arithmetic, or quadratic, which we've seen before. Okay. Now, it could be fun to try to divide things into 3. You can write that code if you want. We probably won't do that in this class. It's an interesting question to see whether that is any better than dividing it by 2. Okay. But here's our divisions and our comparisons, and you can see that we did much, much better on our comparisons. And that's logarithmic because we had a sorted pile of data beforehand. Okay. So a couple observations. Each time we divide by 2. We know something about the cost because we are familiar with the logarithm, right, at this point. And we may still do some work at each level. We haven't seen any algorithms yet that do work at every level. But imagine if I had to do work at every level, right? So if I go all the way back here, probably don't need to go back. If I had to do work at every level, I know I have log base 2n levels. And then I got to figure out how much work am I doing, considering that the size of each level kind of drops in half each time. So there's a number of tricks we'll look at for calculating those things. But that's the real question. It's like, where does the work get done? Okay. So we may have to increment a value. We may have to put something in an array. It really depends on the particular algorithm we're working with. So if I have an cost of n by adding up all of the things across the rows, and I have this many levels, that's broadly speaking how we get to this description called linear arithmetic. That's n cost per level times log base 2 levels of n. That's linear arithmetic. So many of the algorithms we're going to look at are going to have that kind of a cost profile. They might have a 2n cost per level or a 3n cost per level, right? But n will be somehow in that coefficient that precedes the logarithmic term, And that's why we call it linear rhythmic. Okay. So the key maybe to unlocking that understanding is this: how deep does it go? Well, divide and conquer, it's always going to be log base 2 of n. And then there's the adding up of the cost per level, total cost per level, right? All the way from left to right across some level. Okay. So that's kind of our foundational idea for most of our divide and conquer algorithms. Okay. Just figuring out the cost per level is all that's left. So let's take a look at this one. It's kind of a silly program, but what if I said, hey, I want you to add up all the numbers in an array recursively by dividing and conquering. Find a midpoint, right? Recurse or recur is probably the proper way to say it, down the left side, and then recur down the right side. Notice if this could go from 0 to n minus 1, right? Because I got an array with n things, that's never going to be n. It's going to be n minus 1. I don't want to revisit the mid. I already know I looked in the mid over here, and I added what's in the mid, right? So don't add the mid twice. So add 1 to that mid, okay? It's an important insight for your homework too as well, okay? Don't look twice in the same place. Then I return the sum of the left and right sides, and I go up to the next level, not to main, right? Just to the next level. So what's wrong with this? We're missing a base case, right? This function will never finish because we just keep dividing and dividing and dividing, and we never really stop recursing. Okay, so that function will crash if we don't fix that. So let's do this in the code real quick. Let's take a look. And you might want to do this too. It's just good to remember, especially, whoops, when you haven't seen this happen before. But if we run this thing, we should get, if I say 16, I think I'll get a segmentation violation. In C++, that means you kind of tried to go outside of the bounds of the array, probably because you just calculated a midpoint that is beyond, or maybe you just got into an infinite. So what we want to do is just say something like this: if start is equivalent to end, there's nothing to add, so just return ARR of start, okay? So we're not doing any addition there. We're just saying, hey, I only got one number here, so return that, okay? So if I had an odd number array size, then somebody's going to end up like, not having a partner, basically, okay? So now if I say 16 again, the sum of all those 16 ones is 16. So I put it ones in there so it's easier for you to tell you got it right, okay? So it's still probably linear because there's no shortcut to, adding up those numbers. But the way we did it is we went all the way down to the bottom recursively and then added by pairs and then added that up and then added that up. So that's just, getting at the answer a slightly different way, okay? If you wanted to, of course, if you switch the left and the right here, you're going to go down the right side before the left. It's not going to mathematically change the result. But what if we were doing something like dividing pairs of numbers? That's what your lab is like on Thursday. Dividing in pairs will get you a different result if you kind of don't traverse properly. So I'll just toss that out there for you. And, so we start to understand what the ramifications are of swapping these two things, okay? Going down the left first versus going down the right, okay? And remember that this is an implied else for those of you who, maybe have not been coding as much lately. If I return from something, I'm gone, right? If I didn't, then it's kind of an implied else. So you don't have to put that in an else right there. Hopefully everybody sees that. Okay. All right. So getting to it, we'll be diving into the merge sort here shortly. So here's our divide and conquer, right? So if I were to do the addition problem we just looked at, right? We have 0 adds at the bottom. We have 8 adds there, 4, 2, 1. Okay. So if I add up the adds for our total cost, I get n minus 1. Guess what? That's as good as we can do, right? So it shouldn't be a surprise that the number of times we add things together is n minus 1, because that's as good as we can do if we did it linear or if it's divide and conquer or not. But we could, add across the rows, even though we don't do them all at the same time, right? We're doing it left, then right, then recurse back up, left down, two, like this, left that way, right? So this is how we traverse it, but we can imagine it's all there at once and kind of do the math to do a little analysis of our code. Okay. So that's sort of an empirical way of actually doing that. Okay. So we won't get into the theory yet on how we really do this stuff for more complex algorithms, but you can kind of get a sense of the idea of adding across those rows. So let's take a look at our merge sort then. So this is our focus for the day. So not too big of a leap from what we've just looked at. So the idea with a merge sort, again, we're going to talk about the ranges of our array, and I've left out the name of the array here. So we're implying we're going to go from position 0 up to and including position 5. And we're going to need an auxiliary array for the merge sort. So it's like a scratch piece of paper that must be equal to n. So if this is n things, then I need another n spaces to work with over here. Okay. So we're trading in memory to gain speed is the moral of that story, okay? And stability. That's one thing we'll find. So we're going to retain stability. So we're going to do a divide and conquer. We're going to go all the way down to the bottom until we only have one thing and one thing, and we're going to put them in order, and then we're going to go back up. And then we're going to do that with the neighbors, put those two in order, and then we're going to go back up and we're going to merge this into this. So we're going to kind of do little mini sorts and then smush them together. It's a lot easier putting things together that are pre-sorted than things that are fully random. We'll see that here in just a second. And we can do this recursively or in a loop, but I think the recursive part in some ways is a little bit easier to visualize, okay? Now, so there'll be some questions on quiz 2. You got some time to address this or get used to it, but this unwinding part is an important part of the course. So hopefully you can kind of pick up on that. So what do we mean by base merge or merge base? I apologize. I kind of do these things interchangeably. So I have a left side and a right side. Notice the left side is sorted and the right side is sorted. So this is as if we're returning from a deep recursive work. We've already done our hard work on the left and the right. We're somewhere in the middle of the process. And now it's time to smush the left and the right side together. And actually, we're at the end of the process in this case. So if this is all the data we have, then we just got one more thing to do. We need to merge the left and right side together. Okay. So the way we do that is just basically to compare the leftmost area, right? And whichever one we choose as being the one that it's copied over, so in this case, the 1, because we're doing an ascending sort, then we move that pointer forward and compare again, okay? So now we take the 2, we move the 2 forward, compare, take the 3, move the 3 forward, 3 pointer forward, etc. So we're not sorting because we already sorted the left and the right side. We're merging, and that is inherently faster. You can see that it's essentially linear, right? So it's not really going to extend beyond us walking across, in the worst case, what you're seeing here, the full length of any one of these things. So once that green pointer slides over, we're done, and we just copy the remainder of what's left, right? Or once any pointer slides off the end, we copy what's left of the other side. So we might get lucky and they might just glue one end onto the other, right? But if they're interleaved, like this is kind of our worst case scenario, we're still in a linear situation, okay? So we only have to do n-1 comparisons in the worst case, okay? So worst case, n-1 comparisons, okay? And the number of copies, including copying the data back to the original array, worst case is 2n. It's n copies to just copy it down, but we got to put it back probably where we got it from. You know, we can't necessarily use our scratch paper to return the answer, if that's what's expected of us, right? Sort it and put it back in here. So it's still linear. So the base merge or merge base is a linear process, assuming we have pre-sorted the left and the right sides at any size, right? And the left and the right sides aren't always going to be exactly equal. One might be one bigger than the other, right? Because of integer division, right? We'll see that here in a second. Okay. But that's our fundamental, that's where the meat happens. So let's try this real quick. And let's do the digital cards today. Whoops. So let's just try this. So I'll do a couple for you here. I won't kind of take up too much of your time, but I think we're going to get you out of here on time. So I'll shuffle my deck. Okay, this up there, pull out some cards. Okay, I think I can do 8 pretty quickly here. So pop them over, sort them. And there's definitely something gained in you doing this. So, you know, I've been practicing this more or less for years. So I'm going to sort these. So left is sorted, right is sorted. Okay. Or that's where I'm going anyway. So I'm cheating here. Okay, we're assuming that's already done. Okay, compare and compare. Pick the smaller one, move it down, right? Or I'll move it up, right? Goes back, right? Compare, compare and compare. Take this one, compare and compare this one. So you can kind of see, comes together pretty quickly. Compare and compare. And in this case, I ran out over here. So all I got to do is just copy over, right? So it's like I'm out. So just finish. Okay, that's even cheaper. So that's like not our worst case scenario. So that's the meat of the algorithm, really, and the rest is the divide and conquer part. So let's take a look at how it looks visually. So I have some array. I say, okay, I kind of want to work from the bottom up. So keep recursing all the way down to the bottom until you have one thing and one thing, right? So we calculate the mid. We pass the information down. So we're really just passing the boundaries. We're not making a copy of the array. So even though I have a picture of the array here, I'm just representing the fact that I've given the boundaries of that array, and I'm going to work locally within those boundaries. Then I divide that, and I pass down those boundaries, and I say, oh, okay, I'm done here, right? I got 1 and 1, so let's just merge those two together in order. And there they are. So I've really just updated these two positions of the array. Okay, so that part is sorted. Now I unwind and I look at the 8. And I say, okay, 8 is inherently already sorted. So how do I merge the 8 with the 3 and the 9? Okay, I do a merge base and I copy that back. Now I have 3, 8, 9. So the left side here is sorted. And we do our typical branching thing. I got to go all the way to the bottom, come back up again, copy that into the top, right? So this gets copied in 1, 2, 7 up here. Now we have our final merge base and we're done. So the yellow stuff here is kind of what we do on the way up. And the blue stuff is kind of what we're doing on the way down, okay? So I'll show you the code here in just a second, but I thought it might be good to see the process laid out this way. Okay. You might think, is that better? Turns out that yes, it is, right? If we're merging from small problems going up, we actually can achieve this n log n cost, which is better than n times n. So this is going to be a faster sort by a large margin than what we actually saw in the other sorts that we looked at so far. So you might find this interesting. You can dig into it if you want, but I also have a video. But if you just come to this is called visual algo. We'll use this from time to time. But if you go to MER for merge sort, that's a different sort than bubble, selection, insert, quick sort. And you just sort, right? And you say show depth. You'll kind of see it's going to bring down a chunk, divide and conquer, merge back the individual pieces in order, consider to merge the 11 in. Then it's going to work on that right side with the 11 and 7, right? Recursively at the bottom, then come back up and then do the merge base with the red portion. So all that gets merged and copied back. Messy stuff, but the code, as we'll see here, is actually fairly elegant. So now the left side's done and off we go, okay? So that's our, kind of visualization of that. And remember, we need auxiliary space. There is a rare algorithm out there. You might be able to find or research. We used to do it as a homework problem, but trying to do a merge sort without any auxiliary space is a fascinating challenge, but we're not going to do that for class. But you might find that to be an interesting thing. And I'm going to skip over the video since we kind of just saw that thing for real. So for the sake of time, I'm going to not go through the card version of this, but it is a good thing to try to do the full merge sort with 8 cards on the table, okay? You need a little bit of a space to work it out. But remember, you need some auxiliary space to actually accomplish the full sort, okay? So it's a bottom-up sort, as you'll see in the code, because we go all the way down to 1 and 1 before we kind of start sewing things together, okay? And if you want to challenge yourself, use an odd number of cards. That always throws a little wrench in the works. Okay, so let's look at the code. Merge sort, here's the data, right? Here's our scratch paper. Remember, arrays in C++ pass by reference. So we do not make a copy of the array. So if you muck up this array in your deep recursive levels, it's mucked up for everybody. So you only want to work on the region you're told to work on, right, at each recursive level. If the start is less than the end, then let's go for it. Let's find a midpoint, drill down on the left side until we get to 1 and 1, and then drill down on the right side, right, and merge base. Okay, let's take a moment on this. What's going on here? So when I call this function at the top level, it feels like a loop. We're just looping down the left, the left, the left, the left. But we know from that factorial example that we're really replicating the function in memory. So we're getting down, 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 and we can't go any further. Okay, well, that's our base case. There's nothing to do. So we just return. There's nothing to do with a 1. You just go back up to when you have a 2. So now we're going to go down the right side, and we probably are only going to go once and find out we have a 1. So now we're ready to merge the 1 and the 1. Okay. Then we pop back up to the previous level, and the process continues. So you kind of got to put this picture together with the code together with the picture we saw of that giant tree, and try to imagine where is the merge base happening. So we'll see here in a second some visual representation of that. Okay, but you can jump in the code and run it, and it will sort all that stuff just fine and do a little bit of stuff for you to calculate analytics. But notice our midpoint. We're not gonna sort the same thing twice. Mid and then mid plus 1 to end. So don't make that mistake if you're doing this in code or looking at a test question or something. Okay, so here's what that looks like. We go all down and down and down. We get to 1, we get to 2, we get to 1, we back up, merge base. That's our merge base function call. And we go up, and we got to go explore the other side, 1 and 1, right? Go back up, put them together, go back up, merge base, right? Go back up, come down the left side, explore the right, Go back up, come down the left side, explore the right. So the pattern is self-symmetric, right? Even if we go all the way over across to the right side of this thing, we'll still explore the left half of that first before we do any of the right, okay? And then finally, we get back up to the top, of course, our final merge base, okay? So we looked at the recursive part of the code. Let's just quick flash and look again at the, the logic and code for doing this, right? If I have an 8 and a right on the left and a 1 on the right, we just got to swap those two things, right? Okay. So if I have 1 and an 8 and 2 and a 7, we're going to loop through like we saw with our little practice card problem and merge those things back in. Okay. So that's going to be our ascended sort. Okay. Or like this. Okay, so you can kind of go in and see how these things kind of lay themselves out. This is by far the messiest part of this code. So, and one of the things, again, we have to remember is we can only do this after we've sort of gotten to all the way to the bottom and we're on the way up. So we're returning to the top of our recursive stack after we've come all the way to the bottom, okay? And we're using auxiliary space. So we're copying this stuff over, right, into, and there's two ways to do this. You can copy it over and then merge back, or you can merge it over and then copy back. So this animation right here says, oh, let's move everything into auxiliary space, and then we'll do the merge back, right? So we'll compare, move it, compare, move one in, compare, move one in, compare, move one in, and so on, okay? And then copy the rest. And that process gets bigger and bigger as we go higher and higher, okay? So there we had 4 compares, and not our worst case for that size event, okay? So here's the pseudocode for this, right? So we're basically saying for k equals start to k less than or equal to the end, copy over into the auxiliary array, right? So we're in some subsection, right? Notice we're not copying over 0 to end. This is something, we tend to get wrong. We're just saying just between start and end, do that copy, then get your left and right pointers set, and then go through, and if left is greater than mid, and this is where the post increment is important, take what's at position right and then increment the pointer after you take the value, okay? It's just a concise way in C++ of changing the pointer after you get its value, okay? Otherwise, get the other one, right? Get it from the left side and increment that pointer, okay? Otherwise, just if you've run out of space on either side, copy it, right? Copy it from one or the other if the pointer has gone beyond the end of where it should be, okay? That's our merge, okay? So more or less what you'll see in actual code, but not exactly 100%, okay? And there's kind of another way of looking at the midpoint and end. Okay. So midpoint is here, right? It's not exactly between two array positions, obviously. So we're not going to have an even number of things on both sides of that division, okay? Whatever that is, okay? Okay. So remember that calculating the midpoint pretty much for all of this class is going to be, end minus start over 2 would be wrong. We really want it to be start plus end over 2, right? That's going to get it for you every time. Some of us, me included at one point, thought that might actually, was thinking vectors for some reason. So we want it to be this way, okay? That's going to get us the midpoint, okay? Okay. Let's see. Right. So probably most of you have gotten over that hump by now, okay? So this is just us dealing with some of the integer math issues, sometimes the midpoint and the end are going to be the same, right? Midpoint plus 1 and end are going to be the same thing. That's okay. Okay. You're not going to really deal with this stuff. We used to do a homework problem on this where these details were a lot more important. So some of this stuff is interesting, but not critical for your survival in this course. Okay. But interesting to note kind of some of the behaviors of this algorithm. Okay. All the different ways that your code could be wrong, I guess I'll say. Okay. Um, So, performance, summarizing. So in our best case situation, n log n. In our worst case situation, n log n. And our average case situation, n log n. So we won't go through all the analysis of that, but we could empirically simulate that, which we won't do. But that's what we call a tightly bound performance profile. So it means that nothing's going to be too out of the ordinary, which is a really highly favorable trait. So we have an algorithm here that is stable, doesn't break stability. It is n log n, best so far. Takes extra memory, which is maybe a problem on a small Arduino, possibly. Um, but it is stable and it is fast. How fast is it? Well, if an average computer, or maybe slightly older, can do 10 to the 8th comparisons per second, probably more like 10 to the 11th, but this is based on 10 to the 8th. Insertion sort for a million things would take 41 minutes. For a billion things would take 80 years, okay? Compared to merge sort, which is 5 minutes. So that is for sure the difference between never and possible. And that's why n log n is so much more important than quadratic if you're dealing with something really, really big like that, okay? So if you're doing computational science problems, big empirical math solutions or iterative math solutions or something like that, you want to be able to do something a lot faster. And sorting is foundational to everything. Video games, the internet, lots and lots and lots and lots of things are based on sorting. So here's that Python thing, by the way, for people who are curious about it. So if I was to jump into this Python program real quick and say I wanted to, do some calculations for estimating what insertion sort would cost versus what a merge sort would cost, I'm just, plugging and chugging those numbers, right? So what would that be? That's going to be for you know, this for these numbers, it's going to take 7 years for insertion sort or 3 seconds for merge sort. So it's just kind of putting the numbers in perspective. Okay, so that is our merge sort. Okay, and you can do some hybrid things. So there's some interesting sorts out there that do some interesting variations or hybrid combinations. So for example, if you get below a certain number of things, rather than going through the sub-recursive levels, just run a quick insertion sort on it and then go back up your recursive stack. So don't go all the way to the bottom, stop short, do a different kind of sorting algorithm, and then return to the top and do the rest the normal way. Okay? So there are lots of things that we could do, and some of them will get us actually some interesting improvements. Okay, kind of depends on the kind of data that you're working with. Now, just as a quick glance, I'm not going to go through this trace, but this is kind of what it looks like if you were to watch the array come together, right? So you're going to do this and this, right? And then you're going to fix those, and then these, right? And the merge sorts happen. And so eventually you get everything sorted down here, okay? So sometimes you'll see what's called a trace, which just shows how the array evolves over time, okay, as we work on the different pieces of it. You can see where our merge is happening. Merge, 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 okay, for a particular place. Okay. Now, if you want to do it from a looped format, you can do it this way. You're still going to call the same merge-based code, but it's going to be dividing and conquering using a double for loop. Now, you might say, hey, wait a minute. I thought you said double for loops are principally quadratic. But notice this one little trick. Size equals size times 2. Size times 2. We are taking bigger and bigger leaps by a factor of 2 inside of each successive for loop. So that is where our divide and conquer comes from. So some quiz questions down the road might have double for loops where we're dividing by 2 or multiplying by 2. So we might need to look a little more closely at what's going on in our for loops sometimes to tell that they are not simply quadratic just because you have 2 for loops there. Okay. So we won't dig into that too much because I want to get into our homework here real quick before we go. So, but we're essentially getting the same result, right? Getting an n log n. We just got about it a different way. So still a good piece of code. Okay. Okay, so homework 2 weeks. Sorry, I took a little long on this one. So this is hopefully a little more entertaining than your usual one. So we wrote a little story, made a little joke. We're going to use divide and conquer to find something in a two-dimensional space. And we're going to have a compass that's going to help us do that. So this is a kind of a secret function that I wrote that knows where the treasure is hidden in a two-dimensional space. And it's not going to tell you where, it's just going to tell you the direction to go into. And our directions are divided into 8, really 7, 8 directions plus it's going to return a number 8 if you guessed it exactly right. So we're going to be in a two-dimensional array, more or less, or an imaginary array looking for this secret thing. And you're going to write a recursive find amulet function that's going to research this two-dimensional space, taking clues from your compass as you go and slowly dividing and conquering in this two-dimensional space until you find the treasure. Treasure is going to be randomly placed every time. You won't be able to know exactly where it is until you find it. And we're going to have a little competition to see who can find it the fastest. Okay. And then you have to describe the performance of your algorithm. Right? So you're going to design an algorithm and then take a guess. It's part of the rubric, and this one does have a rubric. So hopefully you can kind of pick up some clues from stuff we've been talking about so far, but you can always ask questions. Okay. Part of your grade will be based on your performance. So for example, you could just do a random, you could just pick random locations in this 2D grid until you find it, a billion guesses later, but you won't get as good of a grade. Okay. So, there's only so fast you can go. So most of you will score pretty close to perfect on this one. I think you'll figure out the pattern before too long, but let me break it down for you. Here's our wall of scary statues. The treasure is hidden in one of the mouths of one of these statues. We have row 0 through row 99. That's 100 rows, 100 columns. Okay, so you can do the math on that. And our compass we're going to place directly in the middle to start. That's the best place. You don't have to put it in the middle. But when you call your find amulet function from main, you might want to start in the middle. Okay, I'll give you that hint. So let's say row 45, column 45. If the compass tells you 0, that means it is directly above you in the current row your compass is in. If the compass tells you 1, it's somewhere to the upper right, but not in your current row or current column. Hint, okay? 2 is exactly to your right somewhere, etc. Okay? So where folks usually get lost here is they don't quite get my meaning. Like if I say 6, that means it's in this row from somewhere over here, okay? It's not over here, right? It's just over here if it's a 6, okay? If it's a 5, it means it's going to be somewhere down here we don't know, okay? So you can kind of do the math on that. So if it turns out that your compass function returns a 7 because you told it you were in 45 and 45, then you need to go in the direction of the 7. So you need to reduce your search range to be 46 to 99 rows and 0 to 44 columns, okay? So notice that, very key, +1, -1 on the range, okay? fact, this square should end over here. It shouldn't include this thing over here. Right? So divide and conquer, divide and conquer, divide and conquer, and you might get lucky. Like you might check it again on the next recursive pass, get an 8, and then you know you got lucky that day. Okay, you found it at 8. So that is essentially what we're doing. And here's our compass function. You're going to give it a row and a column. If you want debug output, pass true into there. Don't do this. This is for me when I first call the function in the beginning. So you don't need to worry about that. So remember in C++, if your arguments have an equal sign, that means they're optional when you call the function. Okay. So I would suggest you give it a true here, but just ignore that part right there. Okay. So I can say if compass 1020 is equal to 1, it's upper right. Or I could put the true in there if I want debug output that says what it's doing. Okay. And that means the amulet is somewhere greater than row 10 and greater than column 20. If I get a 4 back, it's straight down, and that means it is exactly in column 20. Exactly in column 20, but less than row 10. Okay. That's the key bit right there. Okay. So here's our find amulet function. Sorry, I got some animation out of whack here. So you're going to say, hey, somebody told me where I'm starting, row high, right? And I'm going to pass that, I'm going to figure out my midpoint. I'm going to pass that midpoint into my compass. I'm going to get a direction back, and I'm going to divide and conquer. Recursively call until I figure out where it is, okay? And then return the total number of guesses that you've taken the whole time, okay? Which is a little tricky, but not that tricky, okay? That is homework 2, okay? And debug will help you if you set it to true the whole time, okay? So for your quiz, you got some merge sort stuff out there. You got 2 weeks on this, so this one's not crucial. And I'm not gonna spend too much of your time on your lab. I just want you to implement this recursive function for dividing and conquering to find a secret number, okay, between low and high, okay? Pass in the secret number, pass in the low high, pass in a guess count, and see how long it takes you to find that thing, okay? So all this stuff, all these links are on Canvas. More instructions are on Canvas. And when we come back on Thursday, we'll do quicksort, which is our next recursive sort. Okay. And I will just leave it there and answer questions. Otherwise, I'll see everybody on Thursday. Thank you.